Well, how's everybody doing out there? Well, welcome to day 14 of Corona Online School. So hopefully everybody had a good weekend and is ready to dive into the next chapter here. So hopefully normal distributions went fairly well. And so what we're going to do today kind of ties into the normal distributions. And so this is probably one of the most important things that we're going to actually talk about in all of statistics, which is called the central limit theorem. And so if you remember, I described that normal distributions are kind of the greatest thing ever because like we know what the curves look like, and we've got the empirical rule that talks about the 68, 95, 99.7. We've got nice calculator ways that we can calculate probabilities and find values and stuff like that with normal curves. So the cool thing is, wouldn't it be nice if we could turn everything into a normal curve? And it turns out with the central limit theorem, we actually can do just that. So even if we have data that isn't normally distributed to begin with, the idea with the central limit theorem is that if you take a large enough sample and then take the kind of like the means of all those different samples and then actually like combine those means together, those means from all these different samples actually turn out to be a normal curve. So what we're doing is we're actually taking the means of a bunch of samples, and that's what gives us this nice normal curve. So we don't necessarily have to do that to be able to solve these type of problems, but that's kind of the neat part. So I am going to have you do like a little experiment on your own to try to get the feeling of what it's like to create a normal curve and stuff like that. But the main thing to kind of remember is, and we don't even need that large of a sample, which is the kind of cool part. So by large, I just mean we have to be able to take 30 samples or more. So if we're lucky and we know our data is normally distributed, then you can take any size sample you want. And of course the data is going to be normal because it was normal to begin with. But if you're not sure if the data is normal, or if you know for certain it's definitely not normal, if you take a sample of 30 or more things of this distribution, and then we take the sample means of all those samples. So if we tested 35 things, then we'd have 35 sample means. Those 35 sample means would actually form a normal distribution. And so what happens is the mean of the distribution is actually the exact same as the population mean. So there's no difference whatsoever. So the mean of the original population is the mean of all the samples that we found. So the only thing that changes is the standard deviation actually gets narrower when we do those samples. So in this case, the sigma of x on top, this is our standard deviation from the original, the original population standard deviation. And so the calculated, this is our standard deviation of all the sample means that we calculated. So you can see we take the original population standard deviation and then we divide it by the square root of n. So again, since we're dividing it by some number, it's usually going to narrow it, because this number's got to be bigger than 30. It's going to shrink our normal curve and pull it in a little bit tighter. So, all right, so let me just show you a little quick applet real fast before you go in. I'm going to have you do this illustrating the central limit theorem on your own here. So here's a little applet that kind of gives us an idea of the way the central limit theorem works. So in this case, we're just flipping coins. And so I've got it set up so that the probability of heads is 50%, which is a standard. And so what we're going to do is if we toss 5 coins, for example, let's see. So in this case, we got 2 heads, and we saw that, we've got a dot down here on the bottom that shows us that there's 2 heads. And so if we did this again, now we've done it twice. So this time we had 3 heads, and so notice we've got the 2 and the 3 graphed. And so at the moment, it's not looking very normal or anything. But the idea is, what happens if I keep clicking this draw samples? So actually, let me jump it up so it's doing 5 repetitions at a time, so it'll actually build a little bit faster. So now we went to 9, and so look, we do have one weird one over here on the left, 0. Now if I go up to 14, so remember if we're flipping 5 coins, we'd expect to get about 2.5 heads each time. So what we should notice as this starts to get bigger and bigger and bigger, look, we're getting less and less coins out on the sides and getting more and more coins in the middle. And so, again, it may not look perfect, but if I click this on, it's getting pretty close to normal. You can see, I'm up to 79 samples, so I've got a fair number of samples going on. But I mean, I could keep going and going and going. And we can see, so even though distributing coins is not something that would be normally distributed, for example, if I take enough of these samples and then calculate the sample means, I can force the actual coins to be a normal distribution, and then I can still use my normal CDF and inverse norm to answer all kinds of questions about those. So the big thing about this is we're not going to, calculation-wise, we're not doing anything new. We're still going to use our same normal distribution. The thing that we're allowed to do is if we choose a big enough sample, we can actually basically turn any type of data into a normal distribution by allowing us to look at the sample means, the mean of the sample means, and the standard deviation of the sample means. So it's kind of cool. It's very powerful. So, all right. So let's go back to the document. So what I want you to do is, for an experiment, actually work on this, illustrating the central limit theorem on your own. And so what we've got is all these different recipes. So this bakery or store had 60 different recipes, and it shows how many days that they used each recipe. So I'm assuming the ones that were like 1 day must have been flops, and the ones that were like 6, 11, 5, things like that must have been better, and they used them more often. So go through and calculate the population mean and the standard deviation of these. So in this case, we're only worried about the things in orange in this case. And you can throw it in the calculator if you want, and throw it in 1var stats to calculate your data. Oh, why is that on there? All right. And then after you do that, what you're going to do is use a random number generator to select 5 samples of size n equals 5, and then record the mean of each sample, then copy the means from students around you until you have at least 30. So what we'll do is we'll share our data on this, so that way we can actually collect our 30 samples that we actually need. And so what we're going to do is, for our five sample, our random number generator, we're going to type it in, and you can do this either in Google. I'll show you how to do it. So like we're interested in numbers between 1 and 60. So if you do this through Google, like you can just type in random number generator, and you just put in there like your max. So for us, we've got 1 through 60 is our max. And then we just hit generate. And so that means I would choose number 12 on the list, number 44, 49, 47, and 11. And make sure you just don't get any duplicates. If you get a duplicate, just run it again. And so those would be the 5 numbers that you would use for your sample, and then you would calculate the mean of that sample and the standard deviation of that sample. And we're doing that, and so we're doing 5 samples so we would do 5 samples each, and then we'll post our 5 samples up, and then we'll do this, collect each other's, and then once we get 30 samples, then we can do the next step of this, which is to basically calculate the mean and standard deviation of those 30 sample means. And then again, now we can repeat this process, taking 5 samples of n equals 10. So again, recording the samples. Again, we'll post them up online so we can share our data. And then once we get enough of those, 30 of those, and again, we'll do the sample mean again. Then we're going to draw a histogram for each one of these, just so we can get an idea how it's getting closer and closer to normal, hopefully, as we go along. So the first one will be just the regular one. So it shouldn't be normal at all, because in this case, we're not assuming that it's normal. 7 should be getting closer to normal, and 8 should be even better. It should be even closer to normal by the time you get there. So this way it'll give you a good idea of what's actually going in to finding the central limit theorem, like what the actual theorem is saying. Now for us, we just want to really be able to apply it and know how to use it. But this will be a cool way for you to get introduced to it and stuff like that. So if you get stuck on that when you're working, definitely let me know. Make sure you're posting your data up there, because if we don't get 30 samples, it doesn't help us any. So make sure you're putting your stuff in the collaboration space so we can all work on this. And then once we're done, so pause this, come back when you're done there. So what we want to do is look at some examples of how we would actually use the central limit theorem. All right, so I'm going to do 2 examples, and I'm going to let you try some, so that way we make sure you're on the right track. So in this case, the mean age of college students in 2008 was 25 years. So this is our population mean. So the population standard deviation of 6.8 years. A simple random sample of 64 students is drawn. What's the probability that the average age of the students in the sample is greater than 26 years? So in this case, again, so we've got our mu of x is 25. Our sigma of x is the 6.8, and our n is 64. And what we're trying to calculate is what's the probability that x is greater than 26. So that's our goal. So again, to the original data, we don't know anything whether it's normal, not normal. So at this point, we can't use the normal CDF or inverse norm, any of those things. So we have to turn this into a normal set of data to be able to do that. So this is where we apply the central limit theorem and turn the mean and the standard deviation into a normal curve. So again, all this other stuff would be going on behind the scenes, but we don't have to do that. We just have to turn it into a normal curve. And the way we turn it into the normal curve is we let our mu of the sample means equal 25, because it's the same as the population mean. And then our standard deviation of the sample means is our original standard deviation, but then divided by the square root of n, which is 64. So in this case, we've got sigma of x equals 6.8 divided by 8. And so that would be, oh, I forgot to bring my calculator. Hold on, let me pull up. 6.8 divided by 8 gives us 0.85. So remember when I was telling you it shrunk the standard deviation? That's what I mean. Originally, our standard deviation was 6.8. And so if you were thinking about this from like a empirical rule situation, one standard deviation, we would have added 6.8 to 25. We'd have been the whole way out at 31.8, one standard deviation away. Well, now we've tightened it up, and to be one standard deviation away, we're actually going to be at 25.85. So, I mean, like, we really shrunk the standard deviation down, which is going to give us more accuracy and things like that. All right, so now that we've got our mean and we've got our standard deviation, now we're set to be able to use our normal CDF, because we're trying to find a probability in this case. So our normal CDF, so in this case 26 is our lower bound. So we're going to let 100,000 be our upper bound. 25.85. And so plugging this in the calculator, let's see, what do we get here? So second var's normal CDF, 26, comma, 100,000, comma, 25, comma, 0.85. So it looks like, about 12%, I guess, 11.97. So, well, I'll rate it all out, 11.97. So it's 0.1197, which is going to be 11.97%. So there's about a 12% chance that we're going to have a probability that an average age of students in this sample is going to be greater than 26 years in this case. So, and again, because remember, this is the population mean. The sample mean shouldn't stray that far from it. They shouldn't be that far away. So in this case, it seems like it's small, but then again, it's kind of based on our standard deviation is so small, like in this case. All right, so let's look at example 2, and then I'll let you guys work some here. So if the mean weight of a bull is 1,135 pounds, so in this case we got that, with a standard deviation of 97 pounds, would it be unusual for the mean weight of 100 head of cattle to be less than 1,100 pounds? So this is where stats can be kind of deceptive, because when you look at that, it's like, well, there's only 35 pounds difference between the mean weight of a bull and what we're trying to test out of this 100 head of cattle sample. So you probably look at it and think, it's probably not unusual. So let's test it though. That's why you can't just throw guesses out there. You have to kind of, actually run statistics on it to check and see if that's really true. So in this case, so again, we've got our mu of x is 1135. Our standard deviation of x is 97. Our n is 100. And so again, what we're looking for is less than 1,100. So I'll just go ahead and write that down so I know what I'm looking for. So now again, we're going to apply the central limit theorem. So that tells us the mean of our samples is the same as our mean of our population. Our standard deviation of our samples is our original standard deviation divided by the square root of 100. So in this case, this turns out to be nice because that's just 10. And then 97 divided by 10 is just 9.7. All right. And so let's write down what we're going to type in. So this is a normal CDF. And so again, since 1100 is the upper bound, then that means we want to put something ridiculously low for our lower bound. So negative 100,000, 1100. Our mean is 1135, and our standard deviation is 9.7. So again, you can see that we've really shrunk our mean down, like our standard deviation down. Our standard deviation went from being almost 100 pounds down to about 10 pounds. So that's going to make a huge difference in our outcome. So the other thing to remember here is everybody remember what it means to be unusual. So remember, unusual means we want a probability that's less than 0.05. If it's less than 0.05 or 5%, then we consider that to be unusual. Probably, very unlikely that it would happen. All right, so let's take a look at our data here. Throw it in the calculator, see what we get. Normal CDF, so negative 100,000, comma 1100. Comma 1, was it 35? I can't remember now. Let's see. 35, 9.7. Good. Comma 9.7. Oh, wow. Okay. So when we see something like this, so let me see, 1.54 e to the negative 4. So what this means is, if this notation's unfamiliar to you, so this is scientific notation, 1.5 times 10 to the negative 4, which means that if we want to turn this back into a decimal so that we can read it, then that means we need to start here and then move our decimal place 4 places to the left. So since it's a negative, we've got to move it to the left. If it were positive, we'd move it to the right, but we'll never have a positive doing what we're doing. So in this case, 1, 2, 3, 4. So it looks like 0.00015 would be the probability that if you took 100 head of cattle, took their sample means, it would actually be 1,100 pounds. So this pretty much is way less than 0.05. So this is super unusual. So what that means is one of two things had to happen. So one, either we got really, 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 really unlucky with our sample and chose a bunch of skinny cows, or the original population mean of 1,135 must have been totally wrong to begin with. So that's kind of what happens when you see something like this, where you get these super unusual scores. So either the original population mean was just wrong, like someone predicted and it wasn't even close to right, Or it is possible, like, that maybe your sample was bad, but with 100, taking a sample of 100 head of cattle, like, pretty unlikely that the sample was probably bad. I would say it was more likely that the original mean population was not good for us to get a result like this. So that's what you guys are going to be doing, and this is going to lead us into kind of what the rest of the semester is about, like trying to, give us data, and then we need to try to make predictions about what we think about this data, whether it seems true, false, whatever. So it's kind of fun. This is where our stats really starts to get kind of fun and exciting. So again, if you have any questions, I'll be around all day tomorrow. So there's about 4 or 5 examples for you guys to work on. So again, it's going to run you through all different possibilities of normal CDF, inverse norm, stuff like that. And again, really take advantage of this illustrating the central limit theorem. I think it'll be a good opportunity for you to understand what's going on behind the scenes and why we're able to actually just take for granted that the average mean is the same as the average mean and how the standard deviation gets smaller. So really take that serious. And again, I'll be around tomorrow if you have any questions, or otherwise, good luck.